Hello guys, welcome to my channel. Today we are going to do a new chapter, that is chapter number 2, the polynomials. Okay, let's start it. So first is, what is polynomial? A polynomial in one variable x is an algebraic expression of the form. Polynomials are the algebraic expressions that is in the form just like this. P of x is equal to a to the power an x to the power n plus an minus 1 x to the power minus 1 plus an minus 2 x to the power n minus 2 plus dot 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 plus a2 x to the power 2 plus a1x plus a0. These can be written also in the reverse form like this: a to the power 0 plus a1x plus dot 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 an x to the power n. This polynomial can also be written as like this, where this n is a non-negative integers. This power must never be a negative, or it is in the form of square root or fraction. This must not be in the fraction or root over or negative. And here a0, a1, a2, comma dot 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 an are constants. These a0, a1, a2, a3 dot 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 are also known as coefficient of polynomials. These an minus 1, an minus 2, a2, a1, a0 are known as the coefficient of the polynomials. Next is the degree of a polynomial. The highest power of x in a polynomial p of x is called the degree of the polynomial. Here is a polynomial. Okay, let's give an example. Here is an example of polynomial. 5x plus 1 by 3 is a polynomial in variable x. Here the degree is 1. How do we know that the degree is 1? Since the highest power of x is 1. And here is another polynomial. Q of y is equal to 3y square minus pi by 2 y plus 7 is a polynomial in variable y. How do we know its degree is 2? Because the highest power of y is 2. So the degree of this polynomial is 2. Next is the types of polynomials. First one is known as the linear polynomial. What is linear polynomial? A polynomial of degree 1 is called linear polynomial. If the polynomial has a degree 1, then it is known as the linear polynomial. Example, f of x is equal to thrice x plus 5. Here the power of this polynomial is degree of this polynomial is 1, so it is a linear polynomial. Here g of y is equal to root over 7y minus 1. Here the power of y is 1. So this polynomial is a linear polynomial. Generally, any linear polynomial in variable x with real coefficient is of the form of every linear polynomial is of the form of f of x is equal to ax plus b, where this a and a b are real numbers and this a must not be equal to 0, but this b can be 0, but this a cannot be 0. Okay. Next is the quadratic polynomial. A quadratic polynomial of degree 2 is called quadratic polynomial. If the polynomial has a degree of 2, then it is known as the quadratic polynomial. For example, f of x is equal to 5x square plus thrice x minus 7 by 5. Here this polynomial has a degree 2, so this polynomial is known as the quadratic polynomial. Another example here is 7x square minus 5x. Here degree is 2, so it is a quadratic polynomial. Another example is minus x square plus root over x. Here is degree 2, so it is a quadratic polynomial. Generally, any quadratic polynomial in variable x with real coefficient is of the form, every quadratic polynomial is of the form f of x is equal to ax square plus bx plus c, where these a, b, c are real numbers and this a must not be equal to 0. Next is the cubic polynomial. Cubic polynomials are the polynomials of degree 3. If the polynomials have a degree 3, then it is known as a cubic polynomial. For example, f of x is equal to 8x cubed. Here degree is 3, so it is a cubic polynomial. Another example is 9x cubed plus 5x squared. Here degree is 3, so it is a cubic polynomial. Next is f of z equal to 13z cubed minus 12z squared plus 11z plus 5. Here degree is 3, so it is a cubic polynomial. Generally, any cubic polynomial in variable x with real coefficient is of the form f of x is equal to ax cubed plus bx squared plus cx plus d. Every cubic polynomial is of the form f of x is equal to ax cubed plus bx squared plus cx plus d. Here a, b, c, d are real numbers and this a must not be equal to 0. Okay, next is biquadratic or quadratic polynomial. Here a polynomial of degree 4. If the polynomial has a degree 4, then it is known as the biquadratic polynomial. Roman number 1, example, f of x is equal to x to the power 4 plus twice x cubed minus 7x squared plus 5x plus 3. Here degree is 4, so it is a biquadratic polynomial. Next example is f of z equal to z to the power 4 minus z squared plus 3. Here degree is 4, so it is a biquadratic polynomial. Generally, biquadratic polynomial in variable x with real coefficient is of the form f of x is equal to ax to the power 4 plus bx cubed plus cx squared plus dx plus e, where a, b, c, d, e are real numbers and a is not equal to 0. Here every biquadratic polynomial is of the form ax to the power 4 plus bx cubed plus cx squared plus dx plus e, where a, b, c, d are real numbers and this a must not be equal to 0. This must be only named as the biquadratic, not a quadratic one. Next topic is value of a polynomial at a given point. Okay, if p of x is a polynomial in x, here there is a polynomial of in a variable x and alpha is a real number and here is a real number, that is alpha, then the value obtained by putting x is equal to alpha in p of x is called the value of p of x at x equal to alpha. If the value of alpha is putting instead of x and we get a result, then the result is the value of the p of x at x equal to alpha. For example, if there is a polynomial p of x is equal to 5x squared minus 4x plus 2, here there is a real number x equal to 2. If I replace x with the 2, so we get p of 2 is equal to 5 into, here is x square, so I replace 2 square minus 4x, replacing x with 2, 4 into 2 plus 2. 5 into 2 square is 4, minus 4 2 are 8 plus 2, 5 4 are 20, minus 8 plus 2. Here there is plus, here is plus, so plus 20 plus 2 is 22 minus 8. 22 minus 8 is 14. So the value of p of x at x equal to 2 is 14. Next is the zero of a polynomial. A real number k is said to be a zero of a polynomial p of x if p of k is equal to 0. Here, a real number k is said to be a zero of a polynomial p of x. How can we say that a k is said to? How can we say k is the zero of a polynomial p of x if I replace the polynomial with k and the result we get is 0? Then the number that I put k will be the zero of the polynomial. For example, in the given polynomial p of x is equal to 5x plus 7. If we put x equal to minus 7 by 5 instead of x, then we get P of minus 7 by 5 is equal to 5 into, instead of x we put minus 7 by 5 plus 7, cancelling 5 and 5 we get minus 7 plus 7, cancelling these two we get 0, then we get 0, then this minus 7 by 5 is the 0 of P of x. Here therefore minus 7 by 5 is a 0 of the polynomial P of x. Here there is a note: every quadratic polynomial can have at most two zeros. However, there exists some quadratic polynomial which do not have any real zeros. Example, x squared plus x plus 1. Here quadratic polynomial can have at most two zeros. That is, the quadratic polynomials can have two zeros, one zeros, or 0 zeros, but it cannot exceed 2. Meaning of at most two zeros means it can have two zeros, one zeros, or 0 zeros. However, there exists some quadratic polynomials. Here exists some quadratic polynomial which do not have any real zeros. This quadratic polynomial x squared plus x plus 1 have no zeros, have no zeros here. Next is the geometrical meaning of the zeros of a polynomial. Okay, let's start it. We know that a real number k is a zero of the polynomial P of x if P of k is 0. We already know that if a polynomial k is replaced, if k is replaced with the polynomial with the x and the value we get is 0, then the k is known as the 0 of the polynomial. To understand zeros of a polynomial geometrically, first we will see the geometrical representations of linear and quadratic polynomials and the geometrical meaning of their zeros. Okay, to understand the zeros of the polynomial geometrically, first we will see their geometrical representations of linear. What do you mean by linear? Degree 0 is known as the linear. We already studied it. And for quadratic, degree is 2. And we will be seeing the geometrical meaning of their zeros here. Okay, let's see it. Geometrical meaning of zero of a linear polynomial. Consider a linear polynomial ax plus b. Here a must not be equal to 0. We know that the graph of y equal to ax plus b is a straight line. We already know that here y equal to ax plus b is a straight line which intersects the x-axis at exactly one point, namely minus b by a comma 0. We know that the 0 of ax plus b is minus b by a. We also know that ax, the linear polynomial here, the 0 of the linear polynomial, this ax plus b is minus b by a. How do we know that? If I replace x with the minus b by a, we will get surely 0. A into minus b by a plus b. Cancelling a, we get minus b plus b is equal to 0. So minus b by a is the 0 of ax plus b. So we get only one zeros. Thus, the 0 of ax plus b is the x coordinate of the point where the graph of y equal to ax plus b intersects with x-axis. So, the 0 of ax plus b is minus b by a is the x coordinate of the point where the graph intersects with x-axis. The intersecting point is the 0 of this linear point. You must understand it. Next is the geometrical meaning of the zeros of a quadratic polynomial. For any quadratic polynomial, ax squared plus bx plus c, where a is not equal to 0. We know that a quadratic polynomial is, the equation is ax squared plus bx plus c, and this a must not be equal to 0. The graph of the corresponding equation y equal to ax squared plus bx plus c has one of the two shapes. We already know that the graph of the quadratic equation is of two shapes, which is known as the parabola, which is either open upwards or either open downwards, which is open upwards like this or open downwards like this. This one is the U shape, is known as the parabola, which can be open upwards or downwards, which can be like this, depending upon whether a is greater than 0 or a is less than 0. If a is less than 0, if a is greater than 0, then the shape of the quadratic equation is like the open upwards. If a is less than 0, here we are talking a about this coefficient. If a is less than 0, then the shape of the quadratic equation will be like this, downward. Now, as per the observation about the shape of the graph of y equal to ax squared plus bx plus c, the following three cases arises. Here three cases arises. Case number 1 is if the graph intersects the x-axis at 2 points. Here the quadratic equation intersects the x-axis at 2 points, here at a and a prime, or here it's open downwards or it is open upwards, intersecting the x-axis at 2 points here at a and a prime. Then the x coordinate of a and a prime are the two zeros of the quadratic polynomial ax squared plus bx plus c. So the graph and the x-axis intersects at 2 points. So this quadratic equation has two zeros. Next, case number 2. If the graph intersects or touches x-axis at exactly 1 point, then the 2 points a and the a prime of case 1 coincides. Here the graph of the quadratic equations and the quadratic equations and the graph intersects at only 1 point, that is at a. Here a and the a prime of case number 1 coincide here. So if the graph and the quadratic equations of the graph intersects at only 1 point with the x-axis, then it will have only one zero. Here only one intersecting point a is of 10, and x coordinate of a is the only zero for the quadratic polynomial ax squared plus bx plus c. Here this graph and the x-axis intersect at only 1 point. Also here this graph and the x-axis intersect at only 1 point. So in the case number 2 we got the quadratic polynomial has only one zero. Next is case number 3. Here the graph of quadratic equations and the x-axis does not intersect each other, so this will have no zeros. If the graph is either completely above x-axis, here is completely above the x-axis or completely below the x-axis. It does not intersect x-axis at any point. Here the graph does not intersect at any point. Then the quadratic polynomial ax squared plus bx plus c has no zero. Okay. Next is, thus geometrically we see that a quadratic polynomial can have either two distinct zeros. So we conclude that in the case number 1 we can have two distinct zeros. In the case number 2 we can have two equal zeros, there is only one zeros, and for case number 3 we know that there is no zeros. From the three cases we conclude that every quadratic polynomial can have two distinct zeros, two equal zeros, there is only one zeros or no zero. From this we can say that a polynomial of degree 2 has at most two zeros. In general, the zeros of a polynomial p of x are precisely the x coordinate of the point where the graph of y equal to p of x intersects the x-axis. So this one is an important one. You must know that how can we know the zeros by just looking at the graph. So if the graph and the x-axis, the intersecting point will be the the graph and the the graph and the x-axis intersecting point will give the zero of the polynomial. Note, a linear polynomial can have at most one zero, and a quadratic polynomial can have at most two zeros. Here the linear polynomial can have at most one zero, that is, this linear polynomial can have only one zero or no zeros, and the quadratic polynomial can have at most two zeros, means it can have two zeros, one zeros, or zero zeros. Okay, here it finished.